Sir? Hello, sir? You are in mute, sir.
Unmute பண்ணிடு.
Okay, sir.
Okay.
Sir, shall we start now, sir?
Okay, madam. Screen.
1 second, sir. 1 second, sir. I will stop my screen.
Full screen. இப்போ ஷேரிங் போட்டுடலாம் நம்ம ஷேரிங்கில் இப்போ இருக்கலாம். ஓ
Now you share your screen, sir.
ஷேர் ஸ்க்ரீன். ஓகே. பிபிடி போடட்டுமா? இது மேலே வச்சிடலாம். மேலே வச்சு
Selva, ma'am. Selva, ma'am. Selva, ma'am.
Yes, ma'am.
My voice is audible, ma'am.
Yes, ma'am.
Okay. Sir, shall I start, sir?
Yes, ma'am. Yes.
Good evening, everyone. With the blessings of Goddess Vasavamba, Sri Kanyaka Parameshwari Arts and Science College for Women, Department of Mathematics is organizing a webinar on the topic, an insight to the chemical graph theory and its applications. On behalf of Sri Kanyaka Parameshwari Arts and Science College for Women, I am happy to welcome you all to the webinar. I would like to extend a special welcome to our resource person, Dr. J. Bhaskar Babuji, Associate Professor, Department of Mathematics, Anna University, Chennai, and also welcome all the participants from various colleges. Now I invite Mrs. P. Selva Shankari, Department of Mathematics, to introduce the speaker of the day.
Ma'am?
Yes.
Yes, ma'am. Good evening to one and all attending this webinar. It is a great honor for me to introduce and welcome our resource person, Dr. J. Bhaskar Babuji, Associate Professor from Anna University, for this webinar. Dr. J. Bhaskar Babuji have an excellent academic achievements. He cleared NET with JRF in December 1992 and awarded PhD in graph theory in March 2004. He guided for 31 MPhil dissertations, 60 MSc projects, and 11 PhD candidates. Now he is guiding 5 more PhD students. He gave invited talks and served as a resource person for many conferences, symposiums, seminars, workshops, and short courses. He also honored as a chairperson for many conferences, workshops, and seminars. He is a member of several scientific and professional societies. He is a member of Board of Studies in Vellore Engineering College and Bapatla Engineering College. At present, he is working as an associate professor in Anna University. Today, we are privileged to have an opportunity to listen to him. I request our guests to address the gathering and to give his precious inputs. Thank you.
Participants, 1 second. Participants are kindly note this. Any questions, kindly type in the chat box, which will be addressed in the question and answer session. And also feedback link will be given at the end of the session. Sir, now the session over to you, sir.
Thank you very much. First, let me thank the organizers of Sri Kanyaka Parameshwari College for Women, Chennai, especially Dr. Sudha and the head of HOD, Dr. Rani, and all the entire team is working in this webinar program. So the topic today, this beautiful day, the Graph Theory Day. I congratulate all the people for this joining this particular webinar. This excellent day, 10th June. The reason is you can watch the slide. Kumar, slide. Can you get the slide? Do you get the slide?
Yes, yes, sir.
Professor Sampath Kumar, born in June 10th, 1936. He's a professor emeritus, University of Mysore. Every year, his birthday is been celebrated as Graph Theory Day. And he's one of the important person in my life to introduce me this beautiful subject called chemical graph theory. He handed over his all his work along with the great legends work as a CD in 2005, just before 15 years. He just gave me the introduction. I said, Come on, Bhaskar Babuji, go ahead with the new topic. So I don't want to forget this great eminent mathematician, living mathematician, Professor E. Sampat Kumar. So this is a great opportunity for us on his birthday. Congratulate Kanika Parameshwari College to have this beautiful seminar with this gathering on this day. Fine. So the topic is an insight to chemical graph theory and its application. So I will take into my mind that you're all beginners of graph theory. So I will introduce little graph theory to encourage all our youngsters brush up graph theory, basic ideas from the history, and then quickly go to the organic chemistry, the most famous hydrocarbons, interesting field, level of +2 level organic chemistry, then link with the graph theory, and then come to its application. So that is the roundup today. Fine. So we start with the history. As we all know that the birth of graph theory is due to the famous Königsbridge problem, where Leonhard Euler, the great mathematician, uh, who said that you cannot find solution for that Euler, that Königsbridge problem. The reason he has been mentioned, and a great person Euler is again they call the father of graph theory. Okay, fine. So what is this particular Königsbridge problem? The city of Königsbridge was located on a perigel river in Persia. Okay, it's old Russia. The city is occupied by 2 islands plus areas of both banks and 7 bridges. Let me go to the figure. So this is what the Königsberg Bridge. There are 7 bridges and 2 land areas and 2 islands. The 2 islands, the red colors are the bridges. The problem is that you may be knowing, the problem is that you have to start from one land area and then travel to all the land areas by exactly making one trip on the bridge. Just a minute, there is some disturbance in my slide. I'll just move it. Yeah, fine. Click this. It's not moving. Yeah. So this is a great man Euler. Look at the problem now. So there are A, B, C, D, 4 land areas and 7 bridges, 1, 2, 3, 4, 5, 6, and 7. So suppose you start with the land area B, you go to 4 land areas and come back to the area B, back, but use the bridge exactly once while walking. So this was very difficult for people to do. And finally, Euler decided this plan that he's interpret this problem as a graph problem, later called graph theory. So what he made is he has marked all the land areas as the points, A, B, C, and D, and then the bridges as the lines. So look at this, C is connected with A with the 2 bridges, 1 and 2. So the 2 arcs are then C to A. Then A to B is connected with the 2 bridges. Then C to D is connected with the 1 bridge. So 1 line between A and D. D is connected to C by a bridge, so there is an line, and D is connected to A, B with the 1 bridge. So finally, this is the graph. It has 4 vertices and then 1, 2, 3, 4, 5, 6, 7 edges. So this is what the interpreting a problem. So any problem, physical problem, can be interpreted mathematically, solved, got the solution, and take it back the solution to reality. That's the beauty of graph theory. So only 2 things are there here. One is point and a line. Points are called vertices, the lines are called edges. So this is what the thing. Now, if you look at this graph, look at the vertex C, it has 3 lines incident, 3 bridges. So degree is 3. This vertex degree is 3. This vertex A degree is 1, 2, 3, 4, 5. And here this vertex B degree is 1, 2, 3. So all the vertices are having odd degree. Go back to home. Otherwise, that's all you lost. When you go out of the home, you have to come back to your home. So the degree is 2. Every time when you go outside, you come back, the contribution, the degree is 2, even number. But look at here, the situation in this graph, all the vertices have odd degree. So it is not possible to come back again. So there, Euler has breaked it and said, no, it's not possible to do this job. So there gave the birth of, so suppose if you go and come back, then it's an Eulerian tool or in circuit and so on. This object goes to the beginning of a graph. So the definition later came as a graph has two components, that is vertices and edges. The vertex can be anything, but most commonly collection of letters or numbers, so on. Then the edge set is a ordered pair AB vertices. So fine. So always a figure is best to explain. So here is a vertex A, B, C, D, and A, B, B, C, A, C, and C, D, 4 edges. Okay, and this is a graph, and how you represent this is a graph. Look at this vertex A, B, C, D here. All the vertices are connected to other vertices by an edge. So there is a completeness. If A wants to communicate to B, directly can communicate. A can directly communicate to D. A can communicate to C. Similarly, any vertex can communicate to other vertices directly. Suppose you don't have an edge between A and D here, then you have to communicate through B or through A. That is connected but not complete. So here the concept of complete graph comes into picture. If all possible edges are there, okay, and it is complete graph, directly you can communicate. Here is also a graph, but the edge set is empty. So this is also a graph. So edge set is empty, 4 vertices isolated. It's called isolated vertices. You cannot communicate here. There are 4 components, A, B, C, D. So likewise, the definition goes, if you look at this is a graph which has self-loop. So vertex V2 can make a self-loop here. So this is called pseudo graph and so on. So I will have simple definitions where I'll explain the pictures. It's always best. So this is a concept of subgraph. If it is a classroom teaching, I can take a board and draw the graph and do plenty of things. This is online. Better I explain the concepts wherever I have the figure. So look at this graph with 4 vertices. Here I removed 2 edges, AB and AC, and also removed this vertex D. What happens is it's a subset, like your set subset. It's a subgraph. The right side is subgraph. Okay. So because removal of a vertex, this entire thing will go. And here I removed 2 edges, so it's 2 components subgraph. So this is the idea of subgraph. Fine. So the path of a graph is intuitively clear, but a little hard to pin down formally. Suppose what's a path? Path means walking. So you have a path to walk. Alternatively, you'll have vertices and edges. So I have a path here, V0, V1, V2 up to Vk. Generally, the path graph, this is a P4 example with the 4 vertices. So it will have 3 edges. So alternatively, vertices and edges comes in a path. If I start with if I do a path, I walk and then come back to same, it's become a cycle. Okay, fine. So this is an example of a path. That's a graph. You have a path A, C, D, 1, 2, 3. Length of the path is 3 because there are 3 edges on the path. So length of the path is 3. Fine. So another concept, connectedness. If you look at this graph as a whole, 1 component, but two components are there. This is a graph. So 5 vertices, but this is disconnected because I don't have a path connecting A to D. I have an edge connecting AB, AC, and edge connecting CD, but still it is not connected, because connected means I can have a path joining any 2 vertices. Completeness means connecting any 2 vertices by an edge. That is connectedness. This is disconnected graph. Fine. And about the cycle, you start at a point, come back to the same point. That's called a cycle. Fine. So there are plenty of cycles. I can say ABC is a cycle. I can say ABD is a cycle. ACE is a cycle. Bigger one, ADEC. So I can take cycles. So length of the cycle is the number of edges in the cycle. Then what I said is about completeness. We have another bipartite concept, I think. Yeah, this is a complete graph with the 5 vertices, K5 notation. This is a complete bipartite graph with the 2 component of vertices. That is one, totally there are 7 vertices, 4 vertices V1 to V5 in one side, and another side we have V5, V6, V7. The idea is that we will join the vertices from one side to other side, not among itself. So V1 is connected to all vertices V5, V6, V7. V2 is connected to all vertices V5, V6, V7, and so on. So no 2 vertices are connected by edge here. There is a path joining V5, V6, V5, and V7, but there is no edge directly. Similarly, so I have 2 components, that is U and another one is V. So there are 4 vertices, there are 3 vertices, completeness is there, bipartition is there, do partition into 2 parts, 7 vertices, totally 4 plus 3. So the notation is K4, 3. If I put the direction for the graph, it becomes a directed graph. So that is the idea of the direction. So we have a figure here, A to B and B to A direction is there. So AB is there, then AC is there, CC is there. The self loop CC, any direction CC is there, then DC is there. So this is the idea of direction, very useful concept. Then of course tree, the most important concept in computer science, trees. So all the data are stored in the leaves of the trees. So tree is a connected graph, I can say, with no cycles or acyclic connected graph. And if you have more number of trees, so disconnected trees, it's a forest. Forest, many components of trees makes a forest in reality, also the same. Okay, so here the tree, we have the root, and then these are the leaves, 1, 2, 3, 4. There are 4 roots. This is called special name for this. Degree is 1. I can say pendant vertices. I can say pendant vertices or leaf nodes. Fine. And these are all internal vertices. Okay, this is a root node. So these are the basic things. Put direction, I get directed tree. So red colors are leaves. Root node is there. Fine. Right. Rooted directed tree. I have root, I also have direction. So top to bottom, the flow is there. So this is again useful concept. Fine. Now let us go into our topic, today's chemical graph theory. So to introduce the idea is, what is a chemical graph theory, the concept? See, there's a separate branch of mathematics called mathematical chemistry, where mathematics plays a major role in chemistry, okay, solving the equations, all physiochemical properties and physical chemistry, we require mathematics. Differentiation, integration, plenty of things you would have come across. Solving differential, decaying equation, and radioactive reaction can be converted to differential equation, solved with the boundary conditions, so on. Now, what is this chemical graph theory? So graph theory plays a tool in chemistry also. So it has been seen that plenty of application. We are going to see all those applications in our talk today. So if you start looking into this topic, there is a beautiful journal. Plenty of journals are there apart from mathematical chemistry, Springer. I'll let you know at the end. So the main idea is to introduce topological indices, which is a molecular descriptor associated with molecular structure. Okay. So in order to make easier to you people, coding the chemical structure from molecular graphs, plenty of algebraic concept, adjacency matrix, characteristic, polynomial, Laplacian, so on. So one by one we'll see. So the importance of algebraic concept in chemical graph theory is highlighted to motivate all the researchers in this area today. Fine. So as we know, it has wide application in engineering, physical, biological sciences, and so on. A graph can be used to represent almost any physical situation involving discrete objects with help of the relation between them. Fine. So as we mentioned earlier, degree of the vertex is one useful concept which we require. The minimum degree is delta, maximum degree is capital delta. Quantitative structure activity relationship, one major area in physical chemistry. Quantitative structure property relationship, all these things represent the correlate the activities of the chemical compounds. Fine. Now we go to the carbon. The interesting carbon is found in many different compounds. It is used in food, clothes, cosmetics, gasoline fuels, etc. The most sixth abundant element in the universe. In addition to carbon, a very special element plays a dominant role in life of chemistry. Fine. This is what the atom has 6 electrons. 4 of the electrons are in its valence shell. Fine. So the number is valence is 4. Middle carbon. Okay. 4. Fine. Hydrocarbon, the most interesting topic of our state. Hydrocarbons has only hydrogen and carbon. 2 types of hydrocarbons are there: saturated hydrocarbon, unsaturated hydrocarbon. Saturated hydrocarbon means single bond. So you know very well, if you can recollect, there are 2 carbon atoms. So ethane is an ethane molecule structure, C2H6. So all the 4 valence are saturated by the carbon-carbon, carbon-hydrogen, carbon-hydrogen, carbon. Look at this. I have removed 2 hydrogen atoms from this. Is unsaturated. Why it is unsaturated means you have to balance the outer electron number. So 4. So it has shared here with 2 double bond. So CC double bond, CH, 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 CH. So if we have a single bond, it is called saturated. If we have a double bond or triple bond, it is unsaturated. Okay. But what we require, a mathematician, we are not bothered about double and triple bond. We are bothered only about the link between an atom and another atom. Yeah, it is linked, it is connected enough for me. I want hydrogen and carbon, I want a hydrocarbon. I have the links with the hydrogen carbon. That's enough for me. I am not bothered about whether it's saturated or unsaturated. But the study is saturated and unsaturated. Fine. So the structure we have studied in our +2 and colleges, alkane, alkene, alkyl. General formula of alkane is CnH2n plus 2. So substitute the n equal to 1. It's a methane, CH4. Then ethane, C2H6, and so on. So this is the number n and the number of hydrogen and a formula. It contains single bond. Fine. So the name alkanes, methane, ethane, propane, butane, so on, and decane, so on. Fine. Then I reduce 2 hydrogen, CnH2n, that is the general formula, CnH2n, this is ethane family. Ethane, methane, there is no methane. So ethane starts, okay, propane, butane, ene, prefix is ene. Fine. Then triple bond. So remove 2 more hydrogen, CnH2n plus 2, then CnH2n, then CnH2n minus 2. I got a triple bond. This is called the radical. This is another radical. 2 different radicals, carbon, carbon, triple bond. Keep on changing these radicals. Say if you put methane, ethane, propane, butane, anything, alcohol, aldehyde, ether, whatever you put, hydrocarbon, the oxygen, hydrogen, R. So the structure will, this is the main thing, right? The R can be changed, different compounds will get. Okay, I will explain that in later stage also again. So at that place, I will explain you more about this, how this radical plays, how our drugs are designed, okay, in the lab, okay, and so on. Things are yet to come. So this is the YNE family, prefix alkanes. Fine. To correlate and predict physical, chemical, and biological property from the molecular structure is a very important unsolved problem in theoretical and computational chemistry, environmental chemistry, medicinal chemistry, life sciences as well. So definitely we require a representation of a chemical compound. Okay, the chemistry people are worried about that, how to represent what is the in the periodic table or atomic number, mass number, properties, and so on. But what we are going to do, a representation of an object giving information only about the elements composing it and its connectivity is named as topological representation of an object. So we mathematician, we would like to interpret the paper, the molecule structure. A topological representation of a molecule is called a molecular graph. There we stand. What is a graph? We know. Now, what is a molecular graph? The topological representation of a molecule. This is the molecular graph. It's a collection of points representing the atoms in the molecule and set of lines representing covalent bonds. So covalent, covariant, whatever it is, a double single bond, the carbon, hydrogen are taken. The bonds are represented as lines. The carbon and hydrogen represented as atoms are represented as dots, is called vertices. Now you look at this propane molecule C2H8 in the screen, C2H8. Just put the 3 carbons and the hydrogens are already 8. This is a molecular graph. But for our study, we require only the carbon-carbon skeleton. We deposit all the hydrogen atoms. We remove these hydrogens and see only this will stand. The middle that is going to be P3. This is called hydrogen diploid molecular graph. So in our entire study, we are going to do this, deplete the hydrogen atoms, take only the carbon-carbon relationship. So this is a molecular graph. Now keep in your mind, take the molecular, take the structural structure of a chemical compound of a molecule, mark all the vertices to be your carbon atoms and the links between the carbon atoms as your edges. We get a graph called molecular graph, hydrogen diploid molecular graph. This is about the methane, center carbon, 4 hydrogens. Okay, that is, every carbon atom must have a chemical valence of 4. So whereas every hydrogen atom is univalent, all are closed vertices. Okay, so this is what the figure says. Fine. So the construction and investigation of the topological indices that could be used to describe molecular structure. So what is a topological index? So that is, an index is a number. It's a number, something we are going to find a number. The number is most important today. Everybody has a number now. Everyone in India has a number. I think you will accept it. You have an Aadhaar number. Some way you have a number for you. You have a register number, a voter ID number, your bank number, your PAN number. Everywhere numbers are there, but one number is there, a unique number is your Aadhaar number. So here we would like to have define a number, an index for a chemical molecule. That is called topological index. So how to define? There are plenty of ways the topological indices are defined, and plenty of varieties of topological indices are there. Variety of problems in pure and applied graph theory can be treated and solved in rather efficient manner to make use of polynomials. Polynomial provides both a convenient, powerful mathematical tool and a valuable proof technique in the field of graph theory. Always you see polynomials are very powerful. You want to talk about analytic function, okay, fine, where it is analytic. Okay, the singularity is there. Okay, what about the expansion, the Taylor series, or do you have Lorentz series, or you have a Fourier series? Any type of polynomial will speak louder, because the coefficients of the polynomials will speak about the function, quality of the function. What is the function, which region, what it does. The whole history of the polynomial you can speak with the help of the coefficients of the polynomial. Such things are there. So slowly we will pass on to that idea. Fine. Look at this compound here. Can we name this 1, 2, 3, 4 in the straight chain? So butane. And here in the second position, you have CH3, CH322 dimethane, 2,2 dimethane. Okay, butane, that is the compound. So see what is the graph it is. Look at the graph. It is the graph here. Just a minute. Hello. Fine. So polynomial plays a major role even here in graph theory, in chemical graph theory. So look at the compound here. This is 1, 2, 3, 4 butane, and you have 2 methyls, CH3, CH3. So this is 2, 2 dimethyl. And we are not bothered about the name and other things. We want a graph. Yes, we have taken the carbon skeleton, 4 carbon atoms in straight chain, and 2 in the second position. So this is what we get a tree. So this is your molecular graph now. So how many vertices carbon atoms are there? 1, 2, 3, 4, 5, 6 carbon atoms are there. 6 carbon atoms are there, and then this is the edges 1, 2, 3, 4, 5 edges are there. This is a molecular graph for this particular compound. Fine. Now I am going to prepare a matrix called adjacency matrix. We all know what is adjacency matrix. It's a binary 0-1 matrix. Whenever you have an edge between 2 vertices, I put a 1. When you don't have an edge between 2 vertices, you put 0. So I prepare a 6 by 6 square matrix with the vertices in the row and column and mark 1 and 0. So first row, first column, first row is 0, and here it's 1, then 0. Then V2 is connected with the V1, V3, V4, V5. Okay, so the degree is 4. Watch this figure. Degree is 4. Yeah, so that is 4 ones are there. So if you see, the degree is 2 for V5, degree is 1 for V6. Fine. This is a matrix called adjacency matrix. Fine. So I take the adjacency matrix and then I calculate the characteristic equation. What is called characteristic equation? So if I have a square matrix of order n, then if there exists a non-zero column vector x such that Ax is equal to lambda x, then I say lambda is the eigenvalue and x is the eigenvector. This is the definition of your lambda. Okay, so such a situation exists if a non-zero column vector exists. Ax equal to lambda x. If Ax is equal to lambda x, then I say lambda is the eigenvalue of the matrix A and x is called the eigenvector. And this particular equation, determinant A minus lambda x equal to 0, is called the characteristic equation. So the characteristic equation, if you expand, you'll get a characteristic polynomial. Characteristic equation, you expand, you get characteristic polynomial, and you solve it, you get the characteristic values. So determinant A minus lambda equal to 0 is called the characteristic equation of the matrix A. Fine. We solve the characteristic equation and get n values. They are called the roots or characteristic roots or eigenvalues of the polynomial. Here we are taking the adjacency matrix of the graph G, and I is the unit matrix of order n. So determinant of xi minus j. Fine. So the characteristic polynomial, we are having this type of notation. Chg of x is x power n. The coefficient may be x power n, k1 x power n minus 1, k2 x power n minus 2, so on. So this is the coefficient of the polynomial. That is, we say cxg1, cg2, cgn minus 1, the constant term. It's a constant term. Or simply write like this: sigma k running from 0 to n, c of gk x power n minus 1. It's our style of in chemical graph theory represent the characteristic polynomial. Fine. So what is the beauty of this characteristic polynomial? Maybe we would have been teaching for the students in matrix theory, the characteristic polynomial 3 by 3 matrix. The characteristic polynomial gives the constant term gives the determinant of the matrix, and the first coefficient, highest coefficient here, the second term x power n minus 1 or x squared coefficient in a 3 by 3 gives the trace of the matrix, and so on. So the coefficients gives plenty of information about the general matrix. Similarly, now at this venture, let me put a break and say, go back and see, we started with the chemical compound and hydrocarbon. We interpreted this as a structural formula as a graph, named it as a molecular graph, and then we wrote a adjacency matrix for the molecular graph, and then we expanded the characteristic equation, and then we are at that stage now. Fine. So here this coefficient 0, CG0 is always 1. Okay, it's a monic polynomial. Okay, fine. So let us see a simple graph G. Look at the graph G, V1, V2, V3, V4. We are not taking any chemical compound. We are mathematicians. Now we are starting the abstract work. We take simply a graph G, explore the concept here. So here, this is what we have. Number of edges is here 1, 2, 3, 4, 5. Number of triangle is 2. Fine. Let us see the calculation. So we take the 4 by 4 matrix, such as the matrix of this particular graph, and determine A minus lambda x, determine A minus lambda x, and then expand this. They expand this. What happens is that here we get a polynomial. The polynomial is with the coefficient, the first term x power 4 is there. First term x power 4 is there. Afterwards, we have we don't have x cube term, just 0. C1 is 0. Then the C2 term is number of edges 1, 2, 3, 4, 5. That's 5. And then the last constant term is number of triangles. That is nothing but minus C3 by 2. You can view this expansion. Okay, now the question is, why this is 0? Why it is 0? That is the question now. This C1 is 0 always, because the graph is a simple graph. You know the simple graph, there's no self loop. If you see the original adjacency matrix of this graph, this entire principal diagonal would have been 0. The trace of the matrix was 0. The trace of the matrix is 0. If you go back to the matrix, look at this adjacency matrix, the principal diagonal is always 0. So trace is 0. But trace is 0, the coefficient, the K1 or C1G is 0 always. Because trace is 0, it is 0. Okay. If at least one eigenvalue is 0, the product will be 0. The constant term also will be 0. Here, let us see. Here the constant term is non-zero for our case. But trace is 0 for all simple matrices. So C1 is always 0 for us. Okay, that is the. So it is x power 4 minus 5x square minus 4x. Constant term is 0 here. That means what? At least one eigenvalue is 0. Product of eigenvalue is 0. So two ideas are coming here. Okay, this is sum of the eigenvalues one at a time. Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4, that is 0. That means two eigenvalues occurs positive negative. Positive negative becomes 0. Product of eigenvalues 2 at a time is your minus 5. Sum of product of eigenvalues 2 at a time is this. Sum of product of eigenvalues 3 at a time is minus 4. And product of eigenvalues is 0. This is the algebraic concept behind this. So all the concept there, you can trace back to graph. Now, look at this another example, bipartite graph. It is a bipartite graph. Okay, not complete bipartite graph. Graph. It is not complete. Completeness means what? V3, V5 should be there. That is missing. So I have taken this example. I don't want to take a complete bipartite. I want to take simply a bipartite graph. That will hold even for a complete, the property. What is the property? Look at the matrix, the 1, 2, 3, 4, 5, 5 by 5 matrix. 5 by 5 matrix. This is the lambda, determined A minus lambda x characteristic polynomial. Then you expand it, you'll get x power 5 minus 3x cube plus x. So as usual, x power 4 term is missing because it is not having self loop. Trace of the matrix is 0. Sum of the eigenvalues one at a time is 0. X cube term is there. X power 4 is not there here. That we have to see that x square term is not there. X term is there. Constant term is not there. So sum of product 2 at a time is 0. Sum of the product 3 at a time is 1. Sum of the product, that's the determinant of the matrix, is 0. That means one eigenvalue is 0. Fine. So if you calculate the eigenvalues of this polynomial x power 5 minus 3x cube plus x, the characteristic roots are 0 is there, definitely, because determinant is 0. Then sum of the eigenvalue is 0, minus 1 plus 0 plus 2 minus 2. So one positive, one negative. One positive, it's negative. So these are the 5 eigenvalues. Such a beautiful property. You have an result. A graph is bipartite if and only if xi plus xn plus 1 minus I is 0 for all I is equal to 1. So beautiful result it is, the proof we can give for the proof. So that is the algebra behind your beautiful molecular graphs. Fine. So likewise, we keep the eigenvalues lambda 1, lambda 2 of adjacency matrices. And then we have a result here. It says that two graphs, GA and GB, are isomorphic. Then their characteristic polynomial coincide. The structure is there, okay, preserved, isomorphism is there. Polynomials will be same, no doubt in it. But the converse is not true. What is the converse? If GA and GB are two graphs having equal characteristic polynomial, it is not necessarily true that they need to be isomorphic. So isomorphism leads to common polynomial. But if they have common polynomial, need not be isomorphic. That is the beauty in reality also here. So nature gives us compounds, chemical compounds. You can find isomorphism structure, but otherwise it's not possible. If two are non-isomorphic graphs, GA and equal polynomial, we say that they are isospectral. The name is the isospectral. If they look isomorphism is structure preserving, but polynomial preserved is isospectral. Isospectral. So the chemical graph, look at the chemical graph: 2,3-dimethyl pentane and 2-methyl 4-ethyl hexane are non-isomorphic graphs. So nature, they are two different compounds, but they have same polynomial, characteristic polynomial, x power 9 minus 8 x power 7 and so on. So look at the polynomial and then the graphs. This is a graph for 2,3-di, second portion, third portion, 2-methyl heptane, 1, 2, 3, 4, 5, 6, 7, straight chain heptane, and 2 side. Here in the second portion, a methyl, the fourth portion on ethane. It's 1, 2, 3, 4, 5, 6 hexane. So two different compounds. They have common, what do you say, characteristic polynomial. When you say characteristic polynomial is common, number of vertices should be same. That is no change in that, because power is 9, x power 9. So 9 vertices are there in your graph. With the help of 9 vertices, I can draw different structures. Sometimes the polynomial may coincide, but the compound may be different. So that is the beauty here. Okay. So this isospectral example. Fine. Let us go to more ideas. Graph GA, GB are isomorphic. Then the polynomial coincides. For that small figure explanation, these two are isomorphic. Yes, both are cycles. Both are cycles, but still twisted like this. So look at this polynomial. The polynomial x power 4 minus 4x squared, and this side it is yeah, I am not able to see in the PPT. Fine. Yeah, x power 4 minus 4x squared. Fine. Same. Next. Two graphs have equal characteristic polynomials. Not necessarily they are isomorphic. Look at these 5 vertices are there, but it's disconnected graph. The polynomial is x power 5 minus 4x cubed minus x power 4. Okay, and this graph is totally non-isomorphic, same polynomial. So we can always think of structures like this. Fine. Okay. No, I don't want to entertain. Fine, I'll go ahead. Next. Graph polynomials are frequently used in chemical applications of graph theory. Here we shall see the main directions in theoretical chemistry in which the graph polynomials are some relevance. Hunkel molecular orbital theory are related to some electron models and concerned with the topology of conjugated molecules. Similarly, the theory of aromaticity, class theory, and so on. So monomer dimer model, higher topological indices, and so on. So I will go into the main details now. Fine. So these are the theories which I spoke to you in the previous slides. The zeros of the polynomials are nothing but the eigenvalues and so on. So they are also called the spectrum of graph theory in theoretical chemistry, okay, which gives the relationship between the eigenvalues. Spectral graph theory is a separate area. Fine. According to Fibonacci's theorem, the limits of the graph spectrum are determined by maximum valency of the vertex D max of the graph. So the valency that is of a vertex that is D max, this eigenvalue lies between minus D max to plus D max. Negative side of maximum valency, minimum valency, maximum valency. Mathematicians always worried about the boundaries, limits, lower bound, upper bound. These are the most interesting thing when you do analysis, which is the smallest value, which is the largest value, and so on. Equality is achieved in the right side if all the vertices in the graph have same balance, and equality is achieved in the left side. Okay, non-isomorphic graphs may be a process of identical structures, polynomial hence mean spectrum. Fine. So, what are the various types of topological indices? Two types are there. One is distance-based topological indices. To name few, it's the Wiener index, edge Wiener index, terminal Wiener index, Harare index, reverse, and so on. This is the list. The list continues with about more than 40, 50 indices related to distances. Fine. Topological indices based on connectivity, Zagreb, reformatted index, no problem, augmented index, and so on. Fine. Look at this great man, Harold Weiner, who in 1947 introduced two terminologies, namely path number and polarity number. So, topological indices of the graph is an invariant number calculated from a graph representing a molecule. Okay. So, the path number was later termed as Weiner number. Well, look this equation T equal to AW plus BP plus C. Weiner predicted the boiling point of hydrocarbon by a linear formula. The relation with the boiling point of an alkane is the Weiner index, constant time energy AW, constant times polarity number BP, and plus C. So this is a very linear relationship. T is equal to AW plus BP plus C. It's on a plane. Fine. So this is where we get the hold, where how you are able to relate the topological index, namely the Weiner index, the first Weiner index, okay, and another distance relation, polarity number, with the help of the boiling point of an hydrocarbon, the most important point, the link between chemistry and your mathematics. So what is this particular index, Weiner number, Weiner index of graph? Weiner index of a graph is defined as the sum of the half of the distance between every pair of vertices of G. So this is the formula. Double sigma means sum up the distance between vertices, okay, Vi and Vj, I running from 1t and j running from the one, half of this. Or you can alternatively use this formula. W of g is equal to sigma d of Vi Vj, I less than j. So here I am removing this half. It's a repetition, so I put 1 by 2. If I don't want to repeat, I just put I less than j, and then I write W of g is equal to sigma d Vi Vj. Half is removed. So this is the formula. Either you can use this formula or you can use this formula. Both are one and the same. The repetition is avoided here. There is no half, single sigma. The repetition is allowed here, double sigma. So I put a half here. So this is about the Weiner index formula. So I take a graph and then find the Weiner index or Weiner. Okay, I will come to this later, this equation later, inequality later. Look at this. This is a graph. This is a graph to start with 4 vertices, V1, V2, V3, V4. And let us calculate the Weiner index. Let us calculate the Weiner index. Okay, the Weiner index. For that, I have a distance between V1, V2 is 1. Shortest distance between V1, V3 is 2. V1, V4 is 2. V2, V3 is 1. V3, V4 is 1. V3, V4 is 1. I add all this, sum up, sigma d of W of g is sigma d of Vi Vj less than j. Answer is 8. So the Weiner index of this particular graph is 8. The 4 vertices, the Weiner index of the graph is 8. Yes, you just fine. Now let us see. Let us take a complete graph. What is a complete graph? What is a complete graph? A graph which is any two pair of vertices is connected by an edge. So if you calculate the Weiner index For a complete graph, it is n with the n vertices, it's n square minus n by 2. Now, what is the distance between any two vertices? Two vertices, complete graph. They show me that they show. What is the distance between any two vertices in a complete graph? Always 1. It is always 1. Distance is 1. So wherever be the vertex, the distance between any two vertices is 1. So if you sum up 1 plus 1 plus 1, how many edges are there? N C edges are there. N is a complete graph. Fine. Now, let G be a path graph. Let G be a path graph. I want my figure there. Fine. Side. Fine. This is what I want to view because I get. Let G be a path graph. If we calculate, the answer is n cube minus n by 6. N cube minus n by 6. Now, what is the distance between a vertex of vertices? It is increasing in a path graph. Suppose I take V1 to Vn. Distance between V1, V2 is 1, V1, V3 is 2, V1, V4 is 3, V1, V5 is 4, and so on. So the distance is more. Sum of the distance number is more, n cube minus n by 6, a path graph. So if you look at the above two expressions, which is small, which is big, this is larger, very large. This is very, very small. So the lower bound is linear index of a graph with the n vertices is a complete graph. The upper bound is given by a path graph. So any graph with n vertices will have a linear index lies between complete graph linear index and linear index of the path graph. So the lower bound is complete graph. The upper bound is the path graph. So that stands the main thing. The what do you say? In this slide, we have shown that the complete graph gets lower, the n vertices are lower bound and upper bound, so on. So that is about the concept of linear index definition and so on. Now, slightly little modified edge linear index. Earlier, we calculated the distance between the vertices. Now, we are interested to calculate the distance between edges. So that was named as edge linear index. So distance between E1, E2, E1, E3, E1, E6, so on. For this graph, it is 31. Then line graph, you know how to draw a line graph. Take the graph, put all the edges as vertices. If two edges are adjacent, then I put a link. That is a line graph T. So for that, the line graph of order T, of order N, we have this answer here. Can you hide this? This is disturbing me. No, this one. Thank you. So if T is a tree of order n, then edge linear index is linear index minus NC2. So NC2 is 15. 31 minus 15 is 6. So beautiful calculation relation between linear index and edge linear index is linear index minus NC2. Fine. So here it is 16. Now comes the polynomial. The polynomial is a linear polynomial graph is defined as W of G Q. Q is the variable here. In the formula is given like this: sigma, the variable Q raised to the power D of UV. Small, short, the distances between U and V pair. Fine. So here, let us look into this example. In the example, how do you calculate the graph, a polynomial, that is linear polynomial? Of course, the linear index of the graph we can calculate. W of G is distance between all the vertices. Once at a time, it's got to be 24. So V1 with the V2, V1 with the V3, V1 with 4. So 1, 2, 3, 2, 1. Then V2 is 1, 2, 2, 1 with the V3, V4, V5. Finally, V6, V1 is 1. Fine. 24 is the answer. Fine. Now, how to go with the polynomial? Use the definition, how to go with the polynomial. W of GQ equal to sigma Q raised per DUV. Now, look at this. Distance between two vertices UV. How many pairs of vertices are there? Distance 1, V1, V2, V2, V3, V3, V4, V2, V6, V2, V1, V2, V1, V6, V6. So there are 7 edges. So there are 7 possibilities. So 7Q. How many vertices pairs are there? Distance 2, V1, V3, V2, V4, V2, V5, this way, V2, V6, V1, V5, V6, V4, V5, V1. So there are 7 pairs again. So this is 7Q square. How many pairs of vertices are there of distance 3? V1, can I say V1, V4? Yeah, both the way, V1, V4. V1, V2, V3, V4, this way or this way. No other possibility is there. This diagonal, V1, V4, distance between is 3. So there is only one possible. So occurrence is only once. So Q power 1 occurs 7 times 7Q. Q power 2 occurs 7 times 7Q square. Q power 3 occurs only once in all possible vertices. So the polynomial, Wiener polynomial of this particular graph is Q cube plus 7Q square plus 7Q. Look at the beautiful concept here. Now stands the calculus here. If I differentiate this polynomial with respect to Q, that is 3Q square plus 14Q plus 7. And substitute the Q equal to 1. What happens is 3 plus 14 plus 7, I get 24. This is nothing but my Wiener number. So from the Wiener polynomial, I'm able to get the Wiener number. So take the Wiener polynomial, differentiate, substitute Q equal to 1, I get the Wiener number. That is the beautiful idea here. Next is idea, terminal Wiener index. Fine. We took a compound. We have interpreted this chemical compound as a molecular graph. We calculated the topological indices, especially the first index called Wiener number. Then later we studied terminal Wiener number. Wiener number can be studied. Wiener index, where it is useful, it is used to predict the boiling point, melting point, molar volume, many physicochemical properties. To predict the physicochemical properties, this index is useful. Every time one cannot go into the research lab, find the melting point or boiling point. So if suppose this topological index is in this range, this melting point will be in this range. So this is a prediction. How your chemical graph theory used to predict certain physical chemical properties, that is the major application to begin with. So slowly we'll go to the next idea, terminal Wiener index. You know what is terminal nodes, leaf nodes. So why do you want to calculate the index with all the carbon atoms? Go only to the pendant vertices. What is the pendant vertices? Degree 1. The pendant vertices is always ready to accept in a chemical reaction. Suppose you take a chemical reaction, 2 compounds join together to form a third compound. There is a possibility it gets joined, otherwise it won't get joined. If it is stable, it is okay, it is a valid lead compound. Otherwise, it is not a lead compound. Fine. What is a lead compound? A compound which is stable and is having some physical properties. It exists. It's a lead compound. Otherwise, the compound will not exist. It's not a lead compound. After some time, it may disappear. It may collapse. It may keep on changing its structure. That it cannot stick with the compound, lead compound. So here, the carbon atom which is kept alone in the pendant vertex, it's ready to attract another carbon atom to join with some other radical and then form a new compound. So what happened? Gutmann, the great chemist and mathematician, living mathematician, about 89 years old, is in Serbia University, Dr. Ivan Gutmann. Even we have some collaboration work with him. In 2009, this distance-based molecular was put forward by terminal Wiener index was introduced by Ivan Gutmann in 2009. So TWG, terminal Wiener index, is nothing but the sum of the distance between all pair of pendant vertices. Why always calculate the distances between the vertices? You can also calculate the distance between the pendant vertices. So that is called terminal Wiener index. The formula stands like this: distance between Vi, Vj, where V, Vj are pendant vertices. Other way is also using the path formula. This is an alternative. Okay, so this idea gave to plenty of applications in chemical graph theory. So I'll go to the next slide. Look at how to calculate the terminal variance index. I'll stick with one formula, easy for you. 1, 2, 3, V3, V5, V4, V6. There are 6 pendant vertices. Of course, 1, 2, 3, 4 non-pendant vertices. So totally 10. Out of the 10, I drop all the vertices of degree more than 2. I take the pendant vertices, I take the degree. I calculate V1 with the V2. Distance is 1, 2, 3. It's 3 here. V1 with the V3, 1, 2, 3, 4. The path is V1, come like this, go like this, and take the answer 1, 2, 3, 4. 4. Then V1 with the V6, V1 with the V5, V1 with the 4, so the distances. Then I go to the second one, okay, V2 with all vertices, V2 with not with V1, of course, it will be repetition. V2 with the V4, V2 with the V3, V2 with the V6, V2 with the V5. So likewise, I have possibilities. The sum is 6, 1, 2, 3, 4, 5 possibilities. V6 is a pendant left out, that's all. So 5 possible sums here. Answer is 51. So now we can say very easily the Wiener index or terminal index is smaller one. Terminal index is smaller one. Earlier Wiener index was a big number because we are calculating for all parameters. Now we are calculating only for the pendant vertices pairs. There are only 6 pendant vertices, so 6 pairs are there. If we are doing it, answer is 51. This is an application, that's application. Okay, immediately as a mathematician, whether the compound exists or not, in the reality, I am a graph theorist. I want to explore the idea on graphs, various graph structures. So thousands and thousands of research papers has been come out for us by the abstract thinking for various structures. So today there is some compound, tomorrow there may be a lead compound. Okay, so that is the business of the drug designer or a chemist to design the various structure. We mathematicians are framing structures using many operations, properties, and so on things in the graphs. Varieties of ideas we get, plenty of structural concepts has been given by mathematicians. Whether in reality it is going to come or not, just hello. Is it clear, madam?
Yes, sir, audible, sir.
Thank you, thank you,
Yes,
thank you.
sir.
No, anything is missing or everything is okay now?
Yeah, we are able to hear you, sir. Please continue, sir.
Okay.
Yeah.
So as a mathematician, we would like to explore the concept on various graph structures. So the first idea is here, plenty of standard graph structures has been already worked out, and this is one result with our team of research scholars in an university. The terminal variance index of a full binary tree. As of our interest, it has given a very difficult to work. It is sigma 2 power L minus 1, sigma m is equal to 110. L is the number of pendant vertices, m into 2 power m. So this is the result here. Fine. So I will skip this result. I'll go to the next. Terminal variance index of G plus. Look at this. Look at this particular graph. The base is a graph G, and then there are vertices V1, V2 up to Vn, and these from these n vertices we have taken new extensions, pendant edge. So V1 dash, V2 dash, V3 dash, Vk dash, and so on. So these are all the new pendant vertices that is linked with the original base vertices V1 to V1 dash, V2 to V2. This graph is always called G plus. That is, for every vertex you add a pendant edge. That is n vertices of the graph. If you take a path graph, you Pn, then Pn plus is a comb graph that you all people know. So G plus is a graph. So what is the beauty here is, originally, whether I have pendant vertices or not in a base graph, I am creating new n pendant vertices from the original graph. That means I am able to attach a methyl molecule, CH3. I have a base compound. I am putting somewhere a CH3, I'm adding to it in one place. Similarly, for all the places, if possible, if I have I remove a hydrogen, I put a CH3. I remove hydrogen. So that reaction is possible for me in lab. If it is possible for me to do for all the CH, all the carbon atoms, everywhere I remove one hydrogen atom, I, I introduce a CH3, a methyl radical inside that. So that looks for me in a graph theory terminology G to G plus. From G, arbitrary graph, adding pendant edge to each vertex, give me a graph G plus. So what is the terminal wave index of this particular graph? So every time I don't want to calculate for a bigger molecule structure, I have a formula in my hand, a general formula in the hand. Of course, you can write what do you say, program to calculate everything. But what is the beauty in this? Writing an algorithm, a program, and then running it and asking the question, and the machine is going to answer. That is not beauty. If you are able to give a structural formula for a structure, then there stands the mathematician. So you have a beautiful theorem, a result with a formula. So what is the use of this? Yes, given an arbitrary graph, if I prepare a new compound, if I prepare a new graph G plus, how it looks like from a atom, from a original organic compound, I am introducing all methyl groups, inserting into this all the carbon atoms, I get new structure. So what is that? That gives me a beautiful terminal linear index of G plus as 2p square minus 2q minus q. What is this p and q? P is number of vertices and q is number of edges. So 2p square minus 2p minus q. Look at the great mathematics in this. The terminal index of a new graph is simply substitute to the original graph. The new graph, you will have p plus p vertices, 2p vertices. The new graph will have p plus q edges, but I don't bother about that. New vertices and new edges. I know the original graph with p vertices and q edges. The resulting terminal wave index is 2p square minus 2p minus q. That is the beauty here. Fine. Next, look at here. I have a graph and have k pendant vertices. By joining the pendant edges to all the pendant vertices successively, several stages, first stage, second stage. So let me think of the graph, a chemical compound. There are 10 vertices and then only 3 pendant vertices. So in reality, what happens? The chemical reaction always the terminal, the end. See, I want to join hand. Breaking the chain and coming in between is difficult compared to the end person joining the hand with the new person. I want to grow the chain. So the 100th fellow will join the 101th person. 101th person will join 102. It goes easy. First person will go to second and he becomes the first later person. So joining hands at the end is easy, the terminal portion. Then breaking the relationship between the middle of the queue and then entering. Anybody wants to stand in the queue, will come and stand. The 120 people are standing, he will be the 121th person. He cannot come, and it's not so easy. If it requires a lot of formality. Similarly, in chemistry also, instead of breaking, if the carbon CH3, the methane group CH4 with one hydrogen depleted, maybe 2 hydrogen goes outside with some oxygen, becomes H2O, water, or whatever maybe the chemical reaction. That is the problem of a chemistry person or a drug designer. So in mathematics here, I want to join again and again on the pendant vertices. So there are k pendant vertices already. I want to put successively. So if at one stage, okay, stop. Enough, my compound is large. This is enough for me for application. I prepared a new compound with the molecular structure like this. Is going to be useful with this because it has this much molar volume. It has this much, a melting point. It has such a property. So let me use it in the drug. So I'll stop. So what is the number? The number is terminal W of old one plus pk into k minus. Look at the beautiful contribution of this mathematics here. Original graphs terminal plus p into k minus. K means number of pendant vertices. How many pendant vertices are there? How many vertices are there in the graph G? So p and k are involved. P, k, and k. So excellent concept it is. A beautiful theorem it is. Next. I have a graph with k pendant vertices and then prepare a new graph joining m pendant edges to each k pendant. These are the 1, 2, 3 k pendants. I am joining m pendant vertices for each one. Look at like it looks like your corona here. Here v1, v2, v3. So in later stage we also for corona products graph theory we have corona product of 2 graphs. I'll come if time permits to those concepts later. So here I have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Everywhere I put 4 this figure. So 4 pendant vertices for each pendant vertex. So what is the result? The result again here possibility is there. I can prepare a new compound using this compound. I can have a new compound, lead compound. That binary terminal variant index is going to be old terminal variant index into m square plus mk into mk minus 1. Such beautiful result. Caterpillar. What is a caterpillar? A graph with the n vertices on the main path. And then you have any number of pendant vertices on the vertices in between. It's called caterpillar. In reality, you know how is a caterpillar. Okay, fine. So here k pendant vertices are there, various positions. Then I have a caterpillar and so on. I think the time is 6:10. I had to quick rush up now with the main ideas. So similarly, I can have terminal vertices of several chemical compounds: 3, 4, 6, 10 tetramethyldecaine. Fine. These are the various compounds prepared with this position is 2, 3, 4, 7, 3, 4, 5, 6, 3, 6, 7, various compounds with the same, what I say, numbers, various compound structures. Fine. And this is for the caterpillar terminal variant index of the tetramethyldecaine compound 98. Fine. Then the another concept, deuter-saturated trees. Deuter-saturated trees are brought like this. A graph is said to be deuter-saturated if addition to any edge results in an increased greater path length. The characteristic of this benzoid graph consists of vertices. Let me show the figure. So this is how the cata condensation. This will be growing. Every time it will be growing with the two branches. So 0th position, 4th, 2nd, and so on. T4n. So for this, we have worked out the terminal indices. Okay. Right. Nanostar dendromer. Dendromer is an artificially manufactured or synthesized molecule built up from branched units called monomers. Nanostar dendromers is a part of new group of macromolecules that appear in photon funnels just like artificial antennas. They gained a wide range of applications in supra molecular chemistry, particularly to host-guest reactions and self-assembly. Fine. This is a nanostar dendromer, and it keeps this structure keeps growing. Okay, the third kind of growth in the structure is given here. Fine. For this, what is the terminal variant index that has been calculated? Fine. So the concept grows reverse variant index. That is the variant index, reverse variant index. This is the formula. So d is the diameter, dij is the distance. Then we have the relation between variant index and reverse variant index. The lambda g is this much minus wg. So reverse variant index of this graph is calculated as 24. Then another reciprocal reverse variant index, do 1 by d minus dij, 1 by rij. Reverse reciprocal index, reciprocal complementary variant index, reciprocal complementary number. This 2,2-dimethyl butane, the molecular graph. So we have a table for this 2,2-dimethyl. Various indices are being calculated, and then we saw this chart, it seems to be a linear relationship. Okay, fine. This is the beautiful concept called energy, graph energy. Some of the eigenvalues is 0, you know, but some of the modulus value of eigenvalues is not 0. That gives the energy of the graph. Beautiful concept. Energy of the graph is sigma determinant modulus lambda. Then comes the distance based afterwards, a degree based. This is called Zagreb index. It is sum of the squares of the degrees of the vertices, sum of the squares of the degrees. So we are able to link this Zagreb index, Yesterday index with the linear relationship that we can see, okay, in the figure. So as we know, we can find the application, quantify the degree of folding long chain molecules, namely proteins, okay, provides to measure average center of complex networks. Okay, so we'll see what is that in the next coming slides. So another way is to find eigenvalues by Laplacian matrices. Laplacian matrix is L is equal to V minus A. A is adjacency matrix, V is degree of the valence. So one can expand this and find the eigenvalues x1, x2, xn. And the Wiener index using Laplacian matrices. Earlier we found the index by distance formula. One can also find from the Laplacian matrix the eigenvalues sigma 1 by lambda I into capital N is the Wiener index. This is another concept, separate study is going on. So these are some compounds where we studied the Wiener index, Yesterday index, energy, and Zagreb and so on. So and found that relation to be linear and so on. Okay, I'll skip all this. I'll go to the Zagreb group of indices. Again, this Zagreb index, I think I have 15 more minutes. I had to wait for the question. So I'll go to the, I'll skip this distance degree based and go for the application. This is to say that Zagreb is also a very old one. It is sum of the squares of the degrees, di square. So for the first graph which you took, it was, I remember, it was 18. The Zagreb index is 18 here. The second Zagreb index and so on. Reformulated Zagreb index, first reformulated. And this is the compound which we took as an example. Methylene cyclopropane. Methylene cyclopropane, in reality it exists. That is this particular compound. Fine. So there goes the study of the Dept, the Wiener index or benzoic acid corresponding molecular graph. It's 42. And then we come to conclusion. The Wiener index is between path and complete again. And this is a caterpillar, 1,4 biregular caterpillar, because degree is either 1 or 4 for this graph. For this, the formula is like this. The Hoffman's tree, and this is a PN. So I will quickly move into all these things are available in internet. You can get the papers from internet for a graph G with at least one vertex of degree P minus in the formula when it is P square minus P minus Q. So likewise, we have a few theoretical results for sum of two graphs operation, so on. So these are the various structures where in reality, if you take this reaction, chemical reaction, if you heat 2 moles of iodobenzene with the copper and presence, endothermic reaction, we get biphenyl compound. So in here, we can use the operation like circle dot. For C6, it's 27. So P2 circle dot is 198. So how the formula is useful in chemistry. So complement of a graph, wherever there is edge, you don't put an edge. Wherever you don't have an edge, you put an edge. That was a separate study, and we got few results. Then in number theory, plenty of results are proved by induction hypothesis. But still, there are a way, even through chemical graph theory, we were able to get some number theory results. That was a miracle for us to work with the congruence relation, other so on things. So that in that way, we found some relations beautiful congruence relations with the modulo 12, modulo 6. The proof is not by induction. Proof is that if you take this is divisible by 12, or the answer is 18n cube minus 162n 192 by 12 was the Wiener index of a graph structure. That by 12 means was divisible by 12. An integer, Wiener index is an integer, so divisible by 12. So that's written as 0 mod 12. Fine. So let us come to some applications of chemical topological indices. So HIV is the most what is a notified disease of this last century, where you don't have medicine like what we have now with the corona, right? So this predicting the anti-HIV activity of quinolol carboxylic acid, that is the main compound which makes the person survive. Okay, but he doesn't die, but he survives with the disease with this particular medicine. The rectovirus, a primary cause of syndrome. Okay, here what plenty of loss we had due to this HIV, and the analysis of this quinolol carboxylic acid using topologies. This Gupta et al. Of team 2012, they suggested a diverse model to predict the HIV integrase activity on a person, how it activates. So in that way, this is the main structure of this quinolol carboxylic acid, the anti-HIV activity. Fine. So R is the radical here in the structure. We keep on trying, see, even for many, disease, diabetics or thyroid problems, we have only 4 or 5 basic medicines. Only the ratio varies. That stands in mathematics. Every time we go for a blood test and we go meet the doctor frequently, 45 days, 60 days, or 1 month, and depends upon the patient's capacity of standing and how the medicine works. The doctor, what he does is the company changes, the medicine ratio changes. That's all. The exact ratio is the only way which cures the person. To make things normal portion. Curing is different from putting in normal. Most of us say, are you sugar in control? Are your thyroid is in control? Only control. Still, we didn't find medicine. Once you find it, you'll get a Nobel Prize. Okay, so still we are able to even enter into what is the problem with the coronavirus, COVID, and so on. Now, look at this quinolol carboxylic. There are 2 R here that keep on changing the R here. Things changes, the medicines changes. So how effective it is, how effective the medicine is going to be, depends upon. So we calculated the Wiener index, thermal index, Zagreb index for all these various type of indices, TW, M1, TFG, flat number, and so on, for various functional group radicals here, substituting for these compounds. There are about 60 compounds. Out of this, we analyzed that the thermal index, Zagreb index, flat number, based on this, the range 2049, above the range were active. Below that, it was inactive. So that is given maybe in this graph. If you see minus, 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 here it is plus. Plus means active, minus means inactive. So where it is active, for which radical, for which number WG, after that, which range that medicine is active, that range, that particular compound is been taken and given for the people. In that way, it is used to predict this. Similarly, the cancer, again another big problem, marine marine pyroxene alkaloids. This is a medicine used to what is say put in normal the cancer activity, and then again it was been studied. A few anti-cancer drugs such as citrabin, vidabin, and vizbin, etc. has been found. This is the main compound 1 and 2. And you are supposed to prepare varieties of compounds in the lab. So whether it's a lead compound, then they stick with it. If it's not a lead compound, if it's not stable, they throw it in the dustbin. Otherwise, they keep it and then do research on it. So predicting the various physical properties, our tools are useful. So 60 compounds containing the pyridoxine alkylate was used to investigate the structure activity relationship using these type of indices. Again, in the lab, we were calculating the various indices in the table: active, inactive, and the range was being fixed. Accordingly, the lead compound was investigated and been done. So again, the analysis of data for the 60 compounds, 30 compounds were active and 28 compounds are inactive. The active range of Venn index from 700 to 2218 and so on. This is the data, and all this is available in the net. You can see that papers. Okay. As the time is getting very close, I have to give some time for question. Then the concept of in further research in other problems are this, which I don't have now. These are the books could be referred in chemical graph theory. Chemical graph theory, introduction, fundamental of mathematical chemistry, and so on. And indeed, this is available in internet. This is available. Earlier, it was in the IIT Madras Library and Institute of Mathematical Science, Tharmani. This is a basic book for Sardi, not in print, but available in IIT. These are some papers, research papers, along with my research scholars. Started the work in when Kumar has given me the CD in 2005. So I changed my, shifted my idea working with students with chemical graph theory from graph labeling, and this some list of obligations. Free access, you can see. I type my name in the Google. I can see that one with the Gutman, the legend Ivan Gutman. Two more papers are there yet to come with Gutman. The journals. This is free access journal, MATCH, Math Communications in Mathematical and in Computation. This is free access. Plenty of papers, interesting papers are coming. Free access. Mathematical chemistry, discrete applied mathematics, so on. And I'm ready to answer you any doubts you have or any suggestions. Thank you very much for listening patiently. Thank you, one and all. Happy Graph Theory Day. Yeah.
Thank you, sir.
Thank you.
Thank you, sir, for your elaborate presentations.
Thank you, madam.
On the various chemical applications of graph theory. And now we have some questions from the chat box, sir, from the participants.
Okay.
Can I forward, sir? Can I forward to you?
Please forward it to.
Yes, sir. Sir, we have a question from Dr. Manigandan.
Okay.
Graph of chromatic numbers and eigen numbers of the graph, is it the same or different?
Chromatic number is different from eigenvalues. This is about topological indices. What we have studied is the number related to a graph. That number can come in different way. One is by distance or by degree, two major areas. Once I draw an adjacency matrix, I go for eigenvalues. Chromatic number is different from these eigenvalues of this matrix.
Yes, sir.
Next.
We have a question from Dr. N. Chandramati.
Okay.
Is it possible to study the topological properties of a molecular structure using graph theory, sir?
Sure. That's what the talk is about. Once you convert this molecular structure into a graph, then you start reading the topological index. Topological index is calculation using graph, distance or degree. Yeah.
Yes, sir. One more question, sir. Whether it is possible to apply fuzzy in chemical graph structures and graph coloring?
Fuzzy is everywhere, but our concept of chemical graph theory is purely interpreting a molecular structure into graph. Fuzzy will not. Yes, fuzzy will not work here because it is chemistry. Crispy is important. If you do fuzzy, then I don't think it will be perfect, because for some other concept you can use fuzzy. Even automata, they started doing fuzzy automata and so on. But when you want to make the real things fuzzy, especially chemistry, what is use of predicting then? So I'm not interested in that fuzzy chemical graph theory, because that becomes more irrelevant to chemistry. Next.
Yes, sir. We have one more question, sir. What is the Wiener index of a caterpillar?
I have put in my slide, right, for a caterpillar.
Yes.
The lengthy formula, you just it is available in the net in my paper. I cannot go to the slide now, right? Do you want me to go to the slide and take it back and tell you? Caterpillar, yeah, we have done it. That theorem, the lengthy formula with the double sigma, with the I and K and so on, number of penalties. Yes, we have to calculate it. Yes, it's there.
Yes.
It's available. It's available.
Yes, sir. Is it possible to trace a graph from characteristic polynomial? Because the characteristic polynomial represents two different graphs.
Yes, yes, it's a very nice question. That's what I said. See, two non-isomorphic graphs, that is isospectral. Two non-isomorphic graphs can have a common polynomial. Reverse process. See, two isomorphic graphs has common polynomial, but the reverse is not possible. Okay, that is not possible because in reality, two different the index or the polynomial comes with the help of the adjacency matrix. So it is not unique. Sometimes you cannot trace, you cannot perfectly go back and say no, not possible. That's called inverse problem. That's called inverse problem. See, given a chemical compound, I can give a number. Given a number, can I give a chemical compound? Means more than one what is a graph structures may come. So that is the problem here. Yes.
Yes, sir. We have a doubt from from Rekha Vinod Kumar. She wants to know the benefits of topological index.
That's what that was my talk, right? My talk in the last 10 minutes. I have given the idea of predicting whether this particular drug which is designed will be active or inactive using the range of the topological index. See, the drugs designed has various topological index, Wiener index, Zagreb index, atom bond index, Balaban index, plenty of indexes are there. Wiener index is most useful. I take the Wiener index, I see whether the drug has the Wiener index falls in a particular range. If it falls in a particular range, it may be active. If it is away from the range, it is inactive. So in that way, for drug designer, it is useful. To predict boiling point, melting point is useful. This is the application of topological indices.
Yes, sir. Can I forward one more question, sir?
Please.
Yes, sir. What is the role of topology exactly in molecular graph? Because we study only the Ruber sheet geometry, and it satisfies three conditions in topological space.
Exactly. Topological. Yes. See, even computer science people, engineering people use the word topology. Network. When you have a cluster of points, how they are related. That is called a topological network. So what mathematician PG students come to know is that topology is a subject, Ruber sheet geometry. That is a subject, fine. But the terminology topology is also used in computer science engineering people and electronic people. So cluster of points related is called a topological network. In that way, it's called topological index. No other relation between your topology and this topological index. Yes.
Thank you, sir.
Thank you.
Now I forward the session to Dr. B. Rani, Head Department of Mathematics.
Welcome.
Good evening to all. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar such a resounding success. On behalf of Sri Kanyaka Parameshwari Arts and Science College for Women, I express my sincere thanks to Dr. J. Bhaskar Babuji for having readily accepted our invitation in spite of his busy schedule. Thank you, sir, for making excellent presentation and making this webinar interesting and meaningful. I also thank all the participants who have participated overwhelmingly and making the event success. I thank our management, honorary correspondent, principal, and vice principals give the opportunity to organize this webinar and for their moral support and guidance. I also thank to our staff members who have made this webinar a great success. Once again, thank you all.
Thank you.
Sir, thank you, sir.
Thank you, madam. Thank you.
Okay, shall we end the meeting, close the meeting, sir?
Yes, madam.
Excuse me, Rani.
One second.
Yes,
hello.
Yes, I'm waiting.
Sudha,
yes, madam.
Regarding the feedback, ma'am. Feedback.
One second. What do you want to say, ma'am?
The feedback link is in the chat box. Participants are requested to kindly send the feedback. Thank you, ma'am. Thank you. Yes, ma'am. Rani, ma'am.
Sudha ma'am. Sudha ma'am.
Yes, ma'am. Yes, ma'am.
We will close the meeting, ma'am.
Yes, ma'am. Yes, ma'am. Thank you, sir.
Sir, thank you, sir.
Thank you.
Thank you, thank you, sir.
Leave பண்ணலாமா ஜென்மா?
Sudha ma'am.
Yes, ma'am. Thank you, ma'am.
We will give 5 minutes for feedback link, ma'am.
Yes, ma'am. Participants, kindly put in your
Note,
feedback in the chat box and also forward through your mail.
We will give few minutes, ma'am, for
Yes, ma'am. Yes, ma'am.
for putting feedback link.
பண்ணலாம். அப்படியா?
முடிச்சிட்டேப்பா, இது வந்துட்டேன்டா, அதுக்காக வெயிட்டிங்ல இருக்கேன். சரியா?
Sudha ma'am.
Yes, ma'am.
Shall I close it, ma'am?
Yeah, we can end the session, ma'am. We thank all the participants, ma'am.
Okay, ma'am. Okay, sir. Thank you, sir.
Thank you, sir.
Shall I end the meeting, sir? Thank you, sir.